Greetings, stargazers, and welcome to our next section on relativity and black holes. And to start ourselves off, we're looking at this amazing picture of the very first image of a black hole. So we'll discuss more about this later in these video series, and let's just dive right into our material. The outline is going to be, we're going to lay out the ideas of relativity. What the heck is it? And we'll do a couple of thought experiments to get a conceptual idea of the ramifications of this theory. Then we'll discuss in detail this idea of this Lorentz factor, and this is a quantity used to measure relativistic effects. After that, we'll talk about the actual evidence for relativity. We're going to do lots of these fun, cool thought experiments, but we also want to know if this stuff is real, so we'll outline some key experiments that help us realize that yes, all these strange, crazy concepts, they are very real, they're very physical. And at the very end, we'll dive into our discussion on black holes, how they're a natural extension of our ideas in relativity, and some fascinating properties. So as usual, let's do just a simple little reading quiz, and I'll ask you, what is the equivalence principle? What does it say? What does it do? Why does it matter for us? So go ahead and pause for a second, hold on here, and now I'm going to dive right in. If you're thinking in a mathematical brain, a lot of you are going to think of this concept of, hey, alpha equals beta, beta equals gamma, alpha equals gamma. And this sounds very mathematical, and the equivalence principle sounds very mathematical too. But I'll tell you, it is not definitely not A. There is related mathematical concepts, but we're astronomers. We want to talk about astronomical and physical idea. So what we're going to say is that when we're establishing the equivalence principle, we're saying what we call your gravitational mass and your inertial mass are equal. Now, if you remember way back at the beginning of these video series, we've discussed this before, but I'll remind you again when it comes up. So let's dive into this theory of relativity. And yes, a large chunk of these ideas are all due to one man, Albert Einstein. Very phenomenal series of works and papers that he came up with. And I'm not going to go over every step, every detail. I'm going to do the highlights. And when we say relativity, there's really only two postulates. To understand relativity, you only need to understand two things. One, the laws of physics are identical in all, quote, inertial reference frames. I don't imagine everyone has any idea or immediate notion of what the heck an inertial reference frame is. So our next couple of slides are going to try and build that up for you. Try and get you thinking these ideas. What do I mean by one reference frame versus another? Now, the other fact that we have to agree on is that everyone, all observers, we must measure the speed of light, c, to be 2.998 times 10 to the 8th meters per second. Most common rounded up to 3 times 10 to the 8th meters per second. These are the only two facts you need for everything we're about to find out and learn today. All reference frames are equal, inertial reference frames. And that the speed of light is constant, and no matter what, everyone will measure that speed. So, with these two postulates in mind, let's start delving into what do we mean by inertial reference frames. And I'm going to use a model of cars driving by. So, we've discussed a lot of things about Newton's laws. Remember, Newton came up with his 3 laws of motions, his laws of gravity. Right? And we say that these laws of physics, they apply in these inertial reference frames. And what I mean is that these are frames that are not accelerating. They could be moving. They could be stationary. But as long as there's no accelerant, there's no net force on you, you are in an inertial reference frame. And so here we have this picture of the red car, blue car, and just an observer on the side. And what's going on here? In this picture, we'll start off with you out here. You're just an observer, you're in a stationary frame, and you're just removed from the cars. And what do you see? You see a blue car going to the left at 25 meters per second. You see a red car going to the right at the same speed. And you see some jokester in the red car, and they threw a ball. And because they threw that ball, gave it some speed, a little bit greater speed in the car, the ball is moving at 40 meters per second. And that's what we observe. And we all agree in these speeds. Well, let's say that your reference frame isn't someone here. Your reference frame is in the red car. How does the world of physics look to you when you're in the red car? You're not accelerating. This is an inertial reference frame. This is totally valid. So what does the world look like in that view? Well, from your perspective, everything's coming towards you. In fact, you're at rest. You're not even moving. The blue car is coming at you at 50 meters per second. Right? So velocity's going back. 25, 25. When we switch our perspective to the red car, this 25 meters per second is just translated to this guy, the blue car. So if you are a passenger in the red car, you see this blue car flying, streaming at you at 50 meters per second. Your prankster friend who's throwing the ball, it's getting away from you at only 15 meters per second. So all we did was go from someone on the sidelines here to someone riding the red car. And already, the green ball is going slower, the blue car is moving faster. Well, continuing on this train of logic, it's perfectly valid to say I'm an observer in the blue car. We all have equal claim to physics. No frame is superior than the other. We all must agree on physics. So, let's move you into a passenger in a blue car. What do you see in this universe? Well, you're at rest, right? The universe is coming flying at you. So you see a red car careening at a fast 50 meters per second your way. And you see that green ball at its fastest speed in any of these pictures. This green ball is flying at 65 meters a second at you. And these are all inertial frames under the guidance of what we call Newton's laws, Newton's framework. So what we're going to do is we're going to repeat this idea of shifting between blue car, red car, or an observer on the side. But we're going to increase the speeds. We're going to make things go a lot faster. And when that happens, the world starts to behave strangely. So remember, we're going to have to start distinguishing between classical and modern physics, or for this lecture specifically, relativity. So let's leave the classical realm and let's go into the relativistic realms. First thing I have to say is Newton's laws, they break down at these relativistic speeds. Velocities are not just going to add up anymore. So here's the picture. You are an observer, relative everything stationary on Earth. And you see the spaceship and the shuttle, they're flying towards each other at half the speed of light. And the spaceship fires a photon torpedo. Well, there's a photon. This thing must move the speed of light. You, the observer on Earth, you see a photon traveling the speed of light. You also see two spaceships flying at each other at half the speed of light. That's what the 0.5 c means. Well, physics is valid no matter what reference frame we're in. No one's accelerating here, so I can jump onto either ship and say, what do they see? So let's jump onto the Enterprise. Jump on the Enterprise, what do I see? Well, the Enterprise is at rest. And my photon torpedoes, well, they're flying off towards the shuttle at the speed of light. The speed didn't change. The fact that that ship is moving in one frame doesn't change the speed of light when I go to another. Alternatively, look at the shuttle. We said in our, going to go back a bit, in our stationary frame, these guys are moving at half the speed of light. And if the cars, we would just add up the velocities. But at relativistic speeds, 0.5 plus 0.5 does not equal 0.8. Speeds do not add up correctly anymore. This is what I mean by Newton's laws are breaking down. In this frame on the Enterprise, you see a shuttlecraft flying at you at 0.8, 80% the speed of light. We could flip frames again, go from the Enterprise onto the space shuttle. What does the space shuttle see? That photon torpedo. No matter what in that picture, that torpedo is always going at you at the speed of light. And now it's the spaceship, the Enterprise, that is flying at 0.8 the speed of light. Like I said, velocities aren't adding up anymore. But all three frames, every frame agrees on how fast light speed is. We may not agree on how fast the others are moving, but we do agree on the speed of light. That's the second postulate. So, special relativity. What it does is it relates events in space and time. We cannot separate them anymore. Everyone must agree on the speed of light, but a consequence of this, they do not have to agree on the lengths or times of measurements. And we're going to do some examples to clarify what the heck that means. And altogether, we'd say that the universe, it exists in this four-dimensional space-time. And that's what this picture is trying to represent here. There's a mass, could be a planet, could be a star. There's some mass there, and the literal fabric of reality warps around that mass. You're going to see lots of pictures that try and play off space-time as this 2D plane, and then you put a mass there and it pinches, it divots the plane down. But the reality is, it's four dimensions. There's this divot everywhere due to the presence of that matter. Matter distorts space-time. So this is our new concept. This is our new way of thinking about what is gravity. In Newtonian physics, we said gravity was this force. Take object 1, object 2, give them some mass, and they must feel a force between them. Relativity says, no. There is this fabric of reality, that's space-time. And these masses bend that space-time. They distort it. And it's that distortions, the curvature of space-time, that give them that effective force towards each other. So we have to get some fascinating insights from this. To start building this up, think about your weight, how heavy you feel when you're riding in an elevator. Right? When you're in the elevator that's not moving, your weight's perfectly normal. You're just waiting for it to go up or down. When that elevator drops, you feel lighter. Right? Think of like riding a roller coaster, if any of you like to do that. Right? When the roller coaster goes over the top of the hill and starts to plummet, you feel lighter. Right? Same thing. If you're accelerating, you feel lighter. If you are accelerating the other direction, then the elevator lifts up. For the roller coaster analogy, that's when you hit the bottom of the hill, start to come back up, and you feel your lunch in your gut go down. Right? So when the elevator's going up, you feel heavier. And then finally, what if you're in free fall? Cut the cable, you would have no apparent weight. So there's this connection between acceleration, what kind of acceleration you have, and your weight. And this leads us to our principle of equivalence. In fact, what we call your gravitational mass, it must be equal to your inertial mass. What do I mean? Put yourself back in that elevator. Put yourself in a box. That box is on Earth. If you toss a ball around, you toss it, you're going to see the motion of that ball accelerate down to the ground. But if you have no image outside that box, this picture is totally equivalent to if you were riding in a spaceship that was accelerating at the same acceleration here on Earth. 9.8 meters per second squared. All right. The way you see the ball move in either gravitational field or a rocket boosting you through space, you feel the same force. And that's what we mean by this gravitational mass and inertial mass are the same. So, with these spooky concepts we're starting to build up, let's get things weird, and we're going to talk about our first thought experiment, the relativistic snake. I love this, guys. This is one of my favorite things. So here's the setup. Here's our first thought experiment. There's going to be this relativistic snake, right? And definition, there's going to have this proper length. This snake has a proper length of 1 meter, and it's going to be sliding across the table at 0.6 the speed of light, 60% the speed of light. Well, there's a snake sliding across your table, so what you're going to do, you're going to take a box, and you're going to try and pick up. You're going to try and drop the box on the snake, pick up the box. Right? So there's two frames of references here. There's your reference. You see the snake coming along, and you're going to try and get the box to capture the snake. There's also the snake's reference frame. What does the snake see? Well, it sees some crazy person with a box flying at them, and they're going to try and drop the box on its head. Remember, we must agree. You and the snake must agree on the speed of light. So let's look at the crazy consequences of this. We'll start at your frame of reference. You see the snake coming towards you. At rest, that snake would be a meter long. But because of its relative speed, it's shortened. What you actually see is a 0.8 meter long snake moving at 60% of the speed of light towards you. You're holding a 1 meter box, so of course you'll be able to drop the box on the snake. Right? The snake's smaller than your box now. But let's go from the snake's perspective. What happens there? In the snake's reference frame, it sees you holding a box that is 0.8 meters long. The snake itself is still a meter. So when you go to drop that box on the snake, what happens? You're going to pinch it. So the snake would declare that there's some box-wielding maniac out there, and if they drop that box on me, they're going to cut off my tail. What in the world's going on here? So, who's correct? In your reference frame, you see a shortened snake. Your box is big enough to hold the snake. But in the snake's frame, it sees a shortened box, and if you drop that box on it, you're going to hurt the snake. So who's correct? Can both be correct? Is this a paradox? A lot of you might want to jump to the conclusion that we've built our first idea of a paradox. Well, one thing of these lectures that I hope to come across to you guys is that there's not a lot of paradoxes here. There's just some weird physics happening. So no, the snake's going to be unharmed, but we need to do a detailed look through of this again. We need to go through this again, but in details. So let's come back to your frame, right? In your frame, you see a snake that has experienced what's called length contraction. Objects that move closer and closer to the speed of light, their length actually shortens and shortens. So from your perspective, you see the snake crawling along, you drop the box hits the ground, and you could pick up the box and the snake just keeps going on by. So we drop the box hits the ground, all edges at the same time. Switch to the snake's perspective. The snake sees that shortened box. In the snake's perspective, the box has gone under length contraction. So when things go by, what the snake sees is one edge of the box hit the ground, then the other edge of the box hit the ground. And then the box goes away behind the snake. I'll do this again. So your frame, you drop the box. Snake is perfectly safe in the box. You lift it up, snake goes away. In the snake's frame, one edge comes down, then the other. You and the snake do not agree on when events occur. We do not agree on simultaneity. We do not agree on what time something happens. Here's a nice pictorial, graphical representation of this. We're going to have a plot of space-time, x and ct, speed times time. And we'll send this white pulse. You send this pulse across. And depending on the motion of the frame, if you're not moving relative to the pulse, everyone at points A, B, and C, we'll go back to the beginning. Everyone at points A, B, and C will agree on this pulse. You can think of it as an explosion happening at the same time. But if you are in a frame that's moving relative to that white pulse, depending on the direction you're moving, you might say the event happens before or after the others. So there is no more concept of simultaneity. We cannot agree on when events occur. So, everyone agrees on the speed of light. Two consequences of this. One, we do not agree on the lengths of objects anymore. And two, we do not agree on when events occur. Summarized here in this nice little joke of a supernova happening. A person on Earth would say that explosion lasted for days, and a person on a rocket ship could say, no, that explosion lasted for seconds. And both are correct.